So let's talk about reduced mass. So if I have these two masses, M1 and M2, and they are attracted to each other through gravitational force, the distance between them is some distance r. So this is the force on 1 from 2, and that's equal to g mass 1 mass 2 over r. And it is in the negative r2 hat direction. This is the force on 2 from mass 1, and that's negative g mass 1 mass 2 over r squared r1 hat. So there is a center of mass between these two, and so we'll just work under the assumption that mass 1 is bigger, so it's going to be closer to it, but it really doesn't matter. It's some position here. This is some distance x. And I know that it's sort of a weighted average, so x is m2r over m1 plus m2. Technically, I'm using this as a reference right here, and it's m2 times r plus m1 times 0 over the total mass. And so this is, so defining this as r1 and defining that as r2. So r2 minus r1 is equal to r. From Newton's second law, I know that F12 plus F21 equals 0. It's because they're internal forces. They should add up to 0. This is M1A1 plus M2A2 equals 0. Well, I have these position vectors. I can do second derivatives here, and so end up with A2 minus A1 is equal to A21. So the acceleration of 2 with respect to x, with the acceleration of 1 with respect to x, or the center of mass. I want to put a c there for that. We can do that more formally, is that the acceleration of 2 with respect to 1 is the acceleration of 2 with respect to x plus the acceleration of x with respect to 1, which is the acceleration of 2 with respect to x, or c, minus the acceleration of 1 with respect to x, or c, which is basically what I've written right here. And this is the force on 2 from 1 divided by the mass of 2 minus the force on 1 from 2 divided by the mass of 1. And from over here, this is the force on 2 from 1 times 1 over mass of 2 plus 1 over mass of 1. Because remember that f of 2, 1 is the negative of f of 1, 2, and vice versa. This is the force on 2 from 1 mass 1 plus mass 2 over mass 1 mass 2. And that's equal to the acceleration of 2 with respect to 1, the acceleration of this with respect to that one. So we end up with the force on 2 from 1 is equal to this mass 1 mass 2 over mass 1 plus mass 2 times the acceleration of 2 with respect to 1. This right here is known as the reduced mass, which often is symbolized by the letter mu. We basically have Newton's second law. So the force on 2 from 1 is equal to mu times the acceleration of 2 with respect to 1. We can look at this slightly differently. The substitution we made, the reduced mass, is m1 m2 over m1 plus m2. So m1 m2 is equal to mu times m1 plus m2, which is mu times the total mass. So when we look at the force due to gravity here, this becomes negative g mu m over r squared r1 hat. So when we go through the Kepler laws derivations, that we assume that mass 1 was not moving at all, but we don't have to. if we had just done mu and capital M here, where this is the total mass of the system and mu is the reduced mass, r is still the distance between them, and then go through the entire derivations that are showing up in the other videos. This would be the full formal way of going about it. And there it is.